Okay, everybody, hello. Welcome to Wednesday, April 17th. We will be continuing with our game theory lesson today after a few announcements. First announcement, it's my mother's birthday. Happy birthday, Mom. Second announcement, it's also my half birthday. Happy half birthday to me. Thank you very much. Your homework is due by 10:30 on Monday, 10:30 in the morning on Monday, April 20th. Your exam is on Wednesday, the 22nd, and that will be open during normal class time. So you should be able to do that during normal class time. And I will be going over the homework on Monday. Monday's lecture will be uploaded around 10:30, and it will be me going over the homework answers. Okay, so today we are starting on normal form games. These are the games that are in this box layout, as opposed to the extensive form games, which are in the game tree layout, which we did last time. Let me get my little notepad out here. Okay. So in these normal form games, we have players moving simultaneously. They essentially, they know what the game looks like. So this game you see over here, this stag hunt game, it's a very famous game. Back when people would hunt stags for fun. And so if you were a player in this game, you would basically be able to see this whole game set up in your brain. You know the possible moves that each player can make. You know that you and the other player each have a choice between hunting a stag and hunting a rabbit. You know all these payoffs here in the middle. But you don't know what moves other people have made because there is no past. There is no having made a move. There's just moves being made simultaneously. Okay. So how do we read a normal form game like this? Let's get a little pen going here. Do gold today. I'm feeling gold. Okay. So these are normal form games in this box form right here. These moves over here are player one. What is going on here? These are player one's moves, and in this game, player one and player two are able to make the same moves. Player one can choose stag or rabbit. Player two can choose stag or rabbit, and we'll go into that a little bit more in a minute. I just want to show you what the setup is like. Okay, so this is player one's side of the square here. This is player two. As you can see, on this game, conveniently, player two's moves are in blue, and player two's payoffs are also in blue. The second player will always have this second payoff number. Okay, so if we end up in a situation where player one is going to play stag and player two also plays stag, then this black 5 right here is player one's payoff, and this blue 5 is player two's payoff. Okay. And that's the same for all the boxes. Player one, player two. They're all. Okay. We solve games like this using a process called iterated dominance. Iterated dominance. Essentially, we're going to compare every move a player could make in response to every move the other player could make. We're going to go one at a time and decide what the dominant moves are in response to every move. Iterated dominance. So I've written the steps out here for you. As you can see, they're pretty repetitive, but it's important to go through them very slowly the first few times you do this. get rid of these other marks I made so we can work. Okay, so the stag hunt game here, it's a famous older game. The setup is, or the story is essentially that you and your very rich friends are hanging out in the British countryside, and one of you says, I sailed, sport, how about we go hunting? And the other one says, well, that's phenomenal. What kind of hunting do you have around here? And then your friend says, well, we have stags and we have rabbits. And so you saddle up the horses. You've got whatever you need to go hunting. I don't know, swords, nets. I have no idea. You have whatever you need to go hunting. You're on your horses and you say, ready, set, go. And in that moment, one of you chooses if you will hunt a stag or if you will hunt a rabbit. And at that same exact moment, the other one makes that same decision, if they will hunt a stag or if they will hunt a rabbit. Similar to rock, paper, scissors, you're making the moves at exactly the same time without knowing what the other person's going to do. Okay. So the story here is that stags are really valuable in terms of hunting. If you get a stag, you get a lot of meat, I guess, but it's difficult to get the stag. You are not able to get it on your own. So you can see here in the game tree that if player 1 tries to get the stag, but player 2 gets the rabbit, player 1's not going to be able to get that stag by himself. That's why we have this payoff of 0 here. Similarly, if player 2 goes for the stag and player 1 goes for the rabbit and doesn't help with the stag, player 2 is not going to be able to get that stag and he's going to get a 0. Okay. But if they both try to go for the stag together, they can work together, they can bring that stag down, and they can share it. Rabbits, much easier to get if you go for a rabbit on your own. You're definitely going to get it, no problem. You can go for the rabbit together. You'll also get it. All right. So let's solve this with iterated dominance. The first thing we're going to do is we're going to have to assume a starting point. All these things are happening simultaneously. We're just going to have to put a pause in this instantaneous gameplay, and we're going to assume that player 1 makes one of the 2 moves available. So assume player 1 makes a move. I'm going to assume that player 1 decides to chase the stag. So if player 1 is definitely going to decide to chase the stag, then this part of the game down here is not going to exist. We're never going to get to this point of the game. We're never going to be operating in these payoff boxes if player 1 chooses to get the stag, because player 1 has not chosen to get the rabbit, and so we're never going to be down here. Okay, so let's assume player 1 decides to get the stag. What's player 2 going to do in response? Now we're playing only in these 2 payoff boxes. Player 1's decided to get the stag. If player 2 joins him and goes for the stag, he will get a payoff of 5. And we're thinking from player 2's point of view now. Player 1 we're assuming, has decided to go stag. That's decided. So now player 2 is thinking, well, if player 1 goes stag, what am I going to do? This is like when you have that argument with yourself or with an imaginary person in the shower, and you just destroy them, right? Well, if they say this, then I'm going to say this, this, and this. And if they say this, I'm going to say this, this, and this. And so player 1 has said stag, and player 2 is thinking, well, if he says stag, I'm going to say stag as well. Because if player 2 goes rabbit, player 2 gets a payoff of 3. 3 is less than 5. We always want that greater payoff. So player 2 is going to go for the stag as well. And I put a little line under there just to mark that that's what we found with that part of iterated dominance. Okay, so that is this first move here finished. Now move on to step 2. Assume player 1 makes the alternative move. So now we're going to assume instead that player 2 has chosen rabbit. And if player 2 chooses to go rabbit, then this top part of the game is essentially dead. We're not going to be up there. Okay, player 2 has chosen to go rabbit, or sorry, player 1 has chosen to go rabbit. Player 2 can either go stag and get a payoff of 0, or go rabbit and get a payoff of 3. Well, 3 is greater than 0, so a little line under that. If player 1 goes for rabbit, player 2 should also go for rabbit. Okay, so that's step 2. Now we're going to do the same thing, but from player 1's point of view. So player 1 is thinking, well, I'm just going to assume, what if player 2 goes stag? If player 2 chooses stag, what should I do? Player 2 chooses stag. That means that this part of the game is essentially dead. We're never going to end up there because we're assuming player 2 is going to pick stag, so we're operating in this column of the game. Player 2 picks stag. Player 1 can choose stag and get a payoff of 5, or play rabbit and get a payoff of 3. Well, 5 is greater than 3, so we're going to go stag on that. Okay, that is step 3. Now step 4. Step 4, same thing, but we are assuming that player 2 is going rabbit. Player 2 is going rabbit. How does player 1 respond? Well, if player 1 plays stag, gets a payoff of 0. Player 1 plays rabbit, we get a payoff of 3. So in this game, we actually are ending up with 2 Nash equilibria, two potential endpoints to this game. We could have a game where both players decide to go for the stag, in which case they'll both get a payoff of 5, or where both players decide to go for the rabbit, in which case they both get a payoff of 3. These are both Nash equilibria. I'm going to write out another vocabulary term here. We have 2 Nash equilibria. And then we talk about our Pareto optimality, right? A Nash equilibrium is Pareto optimal. I'll type that out so we have it quicker. Okay. A Nash equilibrium is Pareto optimal. Yeah. If neither player can be made better off without making another worse off. So which of these payoffs is Pareto optimal? We have one where both players get 3. We have one where both players get 5. They're both Nash equilibria. They're both endpoints to the game that we've found. But this one is Pareto optimal, this 5 and 5. This is the one in which both players are made as well off as they possibly can be without, not at the expense of the other. Okay. All right. I generally won't give you games with 2 Nash equilibria, but I have given you that one. Okay, we're going to do a bunch more examples. Here we have a classic political game. We have our player 1 here is the challenger. This is the new guy that is entering a political race. Got a little player 1 over here. Player 2 is the incumbent. That's the guy who's already holding the position in office. So we have a guy who's in office, we have a guy who wants to be in office, and they have these possible moves they can make. First of all, the challenger, player 1, can choose to enter a political race, or he can choose to do nothing. The incumbent, the guy who's already in office, can choose to accommodate this new challenger, maybe work with him, or can compete with the challenger. Okay, so let's go through our steps and see what we get here. So I'm going to assume a move for player 1. I'm going to assume that player 1 is going to choose to enter the game. And so we will be operating within this smaller portion of the game. We've essentially simplified the game. Oh my God, I can't draw all the way over on this note. Okay, we've essentially simplified the game into a much easier, smaller one that we can solve piece by piece. Okay, so we're assuming that challenger is going to enter. What is the incumbent going to do? Well, the incumbent accommodates, we get a payoff of 1. If the incumbent competes, it gets a payoff of 0. 1 is greater than 0, so if the challenger enters, the incumbent should accommodate the challenger. So we draw a little line under that. Okay, let's choose the other option for player 1. Let's assume that the challenger chooses to do nothing. So now we're operating in this smaller game in these 2 payoff boxes. If the challenger chooses to do nothing, the incumbent can still accommodate or compete, and either way, the incumbent gets a payoff of 2. And we're indifferent between these, so we will write a line under each. If the challenger does nothing, it doesn't matter what the incumbent does. We get a payoff of 2 either way, doesn't matter. So we put a line under both. Okay, now let's do it from the incumbent's point of view. Now player 1 will be responding to an assumed move by player 2. So let's assume that the incumbent chooses to accommodate the incoming challenger. That means we are operating in this smaller portion of the game. If the challenger knows the incumbent will accommodate, will the challenger enter and get a payoff of 2? Or do nothing and get a payoff of 1? Well, they'll enter. 2 is greater than 1. Okay. Assume the other move. Assume that the incumbent will compete, the challenger. If the challenger enters, the incumbent is definitely going to compete because we already assumed that, and the challenger will get a payoff of 0. If the challenger does nothing, the challenger gets a payoff of 1. Again, here we have 2 Nash equilibria. These are just famous normal form examples that I've found online. It's okay to have 2 Nash equilibria. That is okay. We have 2 potential endpoints to these games. Now notice that in this payoff, where the challenger enters and the incumbent accommodates, the challenger has a payoff of 2. But down here, in the other Nash equilibria, the challenger has a payoff of 1. But that's the opposite for the incumbent. The incumbent is better off at this Nash equilibria where he competes. So would it be Pareto optimal? Is this Nash equilibria Pareto optimal? Because it makes the incumbent better off, right? We used to have a payoff of 1 for the incumbent. Now we have a payoff of 2. So is this Pareto optimal? No, because by increasing the incumbent's payoff by 1, we have also decreased the challenger's payoff by 1. Remember, the definition of a Pareto optimum is that neither player can be made better off without making the other worse off. Well, here we're making the incumbent better off, but the challenger is also being made worse off. So there isn't really a Pareto optimum in this game. We have 2 Nash equilibria. Neither is Pareto optimal. Okay. Now I've expanded this a little bit, and I've allowed player 2 to have 3 possible moves. You're going to do the exact same process of iterated dominance here to find the Nash equilibrium. Here we have player 1 has 2 options. Player 1 can choose high or low, and player 2 can choose to play left, center, or right. So I'm going to do iterated dominance here. I'm going to assume that player 1 chooses to play high. So we are operating in this smaller, more simplified game. Okay, player 1 chooses high. What is player 2 going to do? Well, player 1 chooses high. Player 2 can go left, which will give a payoff of 7. Center gives a payoff of 3 to player 2. We're looking at the second number for player 2's payoff. Can play right for a payoff of 3 as well. Well, 7 is the greatest of those 3 numbers, so we can say that if player 1 decides to play high, player 2 is going to go left. A little line under that. Okay, do the same thing, assuming that player 1 goes low to begin with. Player 1 goes low, player 2 can go left, center, or right. Which move will player 2 make? Choose to go left again. The greatest payoff is 6 here compared to 1 and 5. Player 2 is going to go left. Okay, so now let's assume that player 2's moves are fixed and player 1 is the one who gets to respond. So player 1 is thinking in his own private brain, well, if player 2 goes left, what should I do? So player 2 goes left. Player 1 can go high and get a payoff of 4, or go low and get a payoff of 3. 4 is greater than 3. Let's do that one. Okay. What if player 2 decides to go center? Should player 1 play high for a payoff of 7 or low for a payoff of 8? 8 is greater than 7. Put a little line under it. If player 2 decides to play center, player 1 will go low. If player 2 chooses to go right, player 1 is going to want to go high because 2 is greater than 1. This is the exact same process that we did for a 2x2 game. We just had to kind of do it for one more column. So we have a Nash equilibria here at 4 and 7. Just one Nash equilibria, which is nice. This is where the game's going to end up. If you programmed these 2 robots to play this game, and you turned them both on at the same time and said, ready, set, go, they would instantly get payoffs of 4 and 7. Robot 1 would instantly play high, and Robot 2 would instantly play left. Okay. Hey, what does any of this have to do with the spectrum of competition? We're getting there. We're getting there. Okay. The most famous normal form game of all, The Prisoner's Dilemma. The Prisoner's Dilemma. Here's the story behind The Prisoner's Dilemma. There are 2 thieves who have been caught, and so now they are prisoners, and they're in separate rooms being questioned by police separately. If they both confess to the crime, they are both going to go to jail for 8 years. Oops, going to jail for 8 years gives us payoffs of -8. We're losing 8 years. Both confess, both get payoffs of -8. If they both lie and say, that wasn't me, if prisoner 1 in his own room, alone with the cop, says, it wasn't me, and prisoner 2, also in his own room, alone with the cops, at the same time says, it wasn't me, they will get payoffs of -1. However, if prisoner 1 in his own private room alone with the cops lies and says, it wasn't me, but prisoner 2 in the other room confesses, prisoner 2 has essentially turned against his buddy, with or without knowing it, and the prisoner who lied gets a payoff of -10, 10 years in prison, and the one who told the truth gets to go free. Okay. So, if these prisoners were together in the same room and were able to discuss what their plan was, they would decide that they should both lie. They should both lie, say it wasn't them, they get a year in jail, and then they're good to go. They definitely decide that they will not both confess, because they'll both get 8 years in jail. But there's always this possibility that the partner, the other partner, will screw over the other partner. There's 2 partners. If you're one of the prisoners, there's always a possibility that your friend is going to screw you over by confessing, taking the deal for himself, getting 0 years in prison, pinning the blame on you, and you've also lied, so now you get an extra 2 years in prison. There's always that possibility. This game is happening simultaneously. The players are unable to communicate about their strategies with one another. So we can't really have this plan in place or have an agreement in place before we get caught, because this game does not allow for me to beat you up out back after this if you screw me over, or it doesn't allow for me to pay you $100 afterwards if you lie for me. I'm getting a little ahead of myself. Let's solve the prisoner's dilemma using iterated dominance. So let's assume that prisoner 1 chooses to confess. Prisoner 1 chooses to confess. We're operating in this smaller mini game. Prisoner 1 chooses to confess. What does prisoner 2 do? Well, prisoner 2 lies, gets a payoff of -10, or prisoner 2 confesses and gets a payoff of -8. We're going to go for that -8. It's bigger than -10. Okay, we decided that we were going to go here for this -8. Okay, prisoner 1 decides to lie. Prisoner 2 can confess for a payoff of 0, or can also lie for a payoff of -1. Well, 0 is greater than -1, and you can see we're already running into an issue. We just said that if we were communicating with each other, we would both want to lie. But prisoner 2 just had the choice between lying and confessing and chose to confess. All right, let's keep going and see if that's going to come back to bite us. Spoiler, it will. Okay, so now let's assume that prisoner 2's moves are given. Prisoner 2 can choose to confess, and then prisoner 1 can respond from there. So if prisoner 2 chooses to confess, prisoner 1 can also confess, payoff of -8, or prisoner 1 can lie and get a payoff of -10. Well, prisoner 1's going to want to go for that -8 instead of that -10. Okay, assume prisoner 2 chooses to lie. Should prisoner 1 confess or lie? Prisoner 1 should confess to get that payoff of 0, as opposed to that payoff of -1. So how has this happened? We've ended up here where both prisoners get a payoff of -8, even though we just used iterated dominance to make each individual player act according to his own self-interest and maximize his own utility. We've ended up here at this point where both prisoners have a much lower utility than they could have if they communicated. We want to be here. This is Pareto optimal, these two -1s. But we're nowhere near there. We're kind of at the opposite. We're at these two -8s. And why is that? Why did we not end up here? Because we have this little incentive to screw our partner over, to confess if they lie, and to get ourselves that payoff of 0. This is the prisoner's dilemma. How can we make this easier for prisoners? How can we get them to achieve this Pareto optimal payoff? Well, you should let them communicate with each other. Or we could implement a second stage to this game, at which point prisoners can punish or reward one another for their actions within the game. Okay, let's apply this to an oligopoly. We have our two players here. We have firm A and firm B. And firm A and firm B each have options. Firm A can cooperate, or firm A can collude. Same with firm B. I'm going to redraw this using vocabulary we've been using and using the normal form layout we've been using. Let's see. Okay, so firm A, and what are the two things that oligopolists can do? They can collude, or they can compete. Collude means work together. Compete means do not work together. Okay, firm B can collude, work together, or can compete, not work together. I'm redrawing this exact same game down here, just making it a little bit easier to work with. Okay, so let's write out our payoffs here. If both firms collude, both firms get 1,000 buckaroonies. Okay. If both firms compete with one another, they both get 400. Okay, and then we have these mixed strategies here where one firm chooses to collude but the other chooses to compete. If firm A wants to work together but firm B doesn't, firm B is going to get a higher payoff and vice versa. Okay, so I've redrawn this just in the simpler mode that we've been working with. And now let's solve it using iterated dominance and a different colored marker. Use rainbow. What is that? Galaxy? Did I already use that? I already used that. Let's use rainbow. I would never repeat markers on you guys. I respect you too much. Okay. All right, so firm A chooses to collude. Let's make that assumption. Firm A chooses to collude. Firm B's in the shower thinking, man, if firm A chooses to collude, this is what I'm going to do. I'm going to do it right away. And what do they decide to do? They decide to compete. Because if firm B competes, firm B gets a payoff of 1,500. But if firm B also colludes when player A has decided to collude, they only get a payoff of 1,000. Okay. Assume that firm A chooses to compete. What's firm B going to do? Compete for 400 or collude for 200? Compete for 400. A little line under that. Okay. Now we're going to set firm B's moves to be fixed and have firm A respond. Assume firm B wants to collude. Firm A should compete. 1,500 versus 1,000. Okay. Firm B chooses to compete. Firm A is also going to compete. Oh, wait, sorry, that was wrong. Firm A is, also going to compete. So we've ended up in a similar situation as the prisoner's dilemma here. If the firms colluded with one another, they would both get payoffs of 1,000. But instead, they've ended up competing with one another because we have this incentive to compete when the first firm is colluding that's pulling us away from this Pareto optimum up here of each firm getting 1,000. Instead, we're going to end up over here with both firms competing with one another and getting lower payoffs, similar to the prisoner's dilemma. So how do you, as an oligopolist, convince your other oligopolist friends to work with you instead of undercutting you, instead of competing with you? Well, we can introduce multiple stages to the game. That game we just went over is just a rock, paper, scissors style where you ask the firms, would you like to compete or collude? Ready, set, go, give me your answer. And sure, that's part of it. But life goes on after that decision is made. So if you choose to collude and another firm chooses to compete, that's not the end of it. You can punish that firm. You can cut your prices very low and drive that other firm out of the market if you want to. And that other firm knows it. So now that we have this introduction of punishment, of reputation, of the future, the simple idea of multiple stages of a game is enough to incentivize oligopolists to collude with one another. It's enough to incentivize the prisoners to work together to get that higher payoff. This is what is so interesting about imperfect competition when you have a few firms. Monopolistic competition is also imperfect, but we have a lot of firms and they all have their own smaller part of the market, so it's not really worth it for them to communicate with one another. But when we get to this point where we have enough firms that there can be a game, but few enough firms that they can manipulate the market by communicating with each other, we have this super interesting game theory dilemma. Okay. Email me with questions. I absolutely encourage you to look at the genius William Spaniel's YouTube page. He taught me everything I know. It's not really fair. It's diminishing to the many people who actually taught me game theory in university settings and not just on YouTube. But I really recommend that you check that out. If you're having issues, really think about this. This is kind of philosophical. This is where the human aspect of economics comes into play. We're not just doing math over here. We're thinking about human action and human reaction. And that's what makes economics so great and so interesting, and that's why you should be an econ major.